Hello, everyone, and welcome to Func Prog Sweden. My name is Magnus, and I'm the host of Func Prog Sweden. Um, Welcome to a new year. This is the first meetup of this year, so welcome to a new year of functional programming. Um, if this is your first meetup with us here at Func Prog Sweden, we are a meetup all about functional programming, both languages, functional programming languages, and also thinking and doing in other things. As an evidence of that, we have one presentation today in JavaScript doing functional programming and exploring functional programming concepts. So let's head over to the agenda for today. First, I will do a short introduction by me, Magnus. Then we'll head over to local first software development with Elixir by James Arthur. And in this talk, introduces ElectricSQL, a sync engine developed in Elixir, and walks through how you can use it with existing web frameworks like Phoenix to develop local first software. Second presentation, Transforming Composition by Kyle Simpson. One of the gateways to get into functional programming is to discover map, filter, reduce. But that also comes, usually can come sometimes, with various forms of, how should I put it? You can get into various forms of problems, issues, and Kyle will explore these and try to take them down and show you how to do it. In the end, we'll do a post-show chat, as always. But first, also thank you Beat for sponsoring the video stream. Thank you very much. And if you want to know more about Beat, just check them out in social media or on otterbeat.com. And the coming schedule for the spring, for the 2025, 18th of February, we're back. Then 18th of March will be also not just online, but also at Kivra. So if you're in Stockholm, make sure to sign up so you can come to Kivra and visit us in real life. And then in April, we haven't set the date, and also we'll be doing one, of course, in April, May. We haven't set dates yet, so be sure to check out the meetup page when we will update the dates and with the presentations that will come. And of course, you want to support Funkprog Sweden, head over and join us at Meetup, and make sure to subscribe to the YouTube channel. And if you want to chat, ask more elaborate questions than you can do in the YouTube chat, head over to Discord and head over to Meetup, or you can find the invitations link both in Meetup and on the YouTube page to our Discord server. Which brings us over to, if you have any questions, just shoot them in the chat or shoot them on Discord, and I'll take them with the presenters. With that, we are ready to start with our first presentation. Warm welcome, James, to Funkprog Sweden.
Thank you.
Yeah, you're welcome. The stage is yours.
How long have developers been building apps on web service APIs? So writing code like this. I think anyone who's done any kind of web development is used to making this type of fetch request. But then, of course, as we all know, you have to handle all of the failure modes that come with it. So that's like handling the status codes. And if you look at the numbers, like 400 as developers, they're kind of hardwired into our brains, like we know these numbers by heart. There are maybe some fun ones that we might be less familiar with, like 100 continue or use proxy. But basically, we've all written this code here. It's like you make a web request, you're looking at the response. Did it work? Did it go through? Okay, handled the result. If it didn't, what happened? Was it my fault? Was it the server's fault? Should I retry? Do I get the error on the status code, or am I getting it because I stuck a try catch around it and something threw an error? So this is all just very familiar stuff, right? And in a way, this type of fetching methodology, like those status cats are quite cliched, right? They're even super pixelated. They're actually like 600 pixel wide images, and it's an indication that they've been around a while. Like the muscle memory behind this stuff is ingrained, and it's just how you build applications. Well, this talk is about a different way of building software, and it's one where you abstract away this whole domain of fetching and programming across the network, and instead your application code talks to a local embedded data store, and then data syncs in the background. And that way, that paradigm is called local first. So I'm CEO and co-founder of a company called ElectricSQL. Our main product is the Electric Sync engine. So we sync data out of Postgres into wherever you want. So it's mobile apps, web apps, edge workers, working sets, stores, etc. And we also develop a project called PG Lite, which is a lightweight WASM Postgres that you can run in the browser. So you can have Postgres as that local data store inside your local first app. And just briefly, just to be clear, these are composable components, like they work together, but you don't have to use them together. So you can use Electric to sync data from Postgres in the cloud into PG Lite inside the clients, but you can also just use PG Lite on its own, and is an example of Superbase doing so to build database.build, which is a very cool AI-driven database app builder site that they've built on PG Lite. And just as you can use Electric on its own. So you can use Electric to sync into a database, but you can also just sync into something like a JavaScript object or a Redis hash, basically any way you like. And this is an example of Trigger.dev, who are like a background jobs processing platform, and they use it just to sync data into JavaScript in memory for their real-time dashboard. And just to finish the context, we're a startup, but everything is open source, so it's all Apache 2. And you can just get a sense of some of the people behind the company, like we're backed by the founders of Superbase, Cockroach, MotherDuck, Heroku, etc. And also, just to flag it up, by Jose Falim, who, as you know, is the creator of Elixir. And so with this talk, my goal is to first convince you, if you're not already, that local first is a better way of building software. And then I want to show you what we're doing in Elixir at Electric to help you build local first software. And then I'm going to show you how you can use Electric to build local first apps in Elixir and Phoenix today. So let's jump in. Let's talk about local first. One way to think about local first is as the natural evolution, or maybe the natural end game of state transfer. So state transfer, this sort of fundamental concern of how you build software applications, like how do you get the data from the front end to the back end? And if you sort of look at this from a developer experience point of view, it's evolved. Like early on, you didn't have things like Ajax, and then things consolidated on REST, and then GraphQL started this process of abstracting away state transfer out of the application domain. And local first is kind of the natural end game for that. It fully abstracts state transfer out of the application code, so the application code just talks to the local embedded database. And from a UX point of view, if you really boil it down, this is my highly sophisticated diagram of all web apps. Start with the top left. The user clicks on a button, sends a request to the server talks to the database, sends a response back, the user sees the result. And the problem with this is that you have the network on the interaction path. And so as the application developer, you don't control the network. So your availability, the quality of your application's user experience is determined by factors out of your control. And you spend a whole bunch of time coding around the dictates and challenges of this client-server bridge. So authorization, serialization, error handling, status codes, etc. Whereas in comparison with local first, you basically make one small change to the architecture, and that's to move the data store into the front end. And with this, the application code can talk to the local data store first. That's why it's local first. And then the data syncs in the background. And it takes the network off the interaction path. So you don't need to spend all your time coding across this client-server bridge and dealing with all of the problems. And as a result, with your user experience, everything's instant. It's super snappy. You get multi-user collaboration built in through this background sync, and you own your own availability. The apps are super reliable, so they work when they're offline. They work through patchy network connectivity. They're not reliant on the server being online or compatible to keep functioning. And so that's a quick overview of why I'm arguing that local first is a better way of building software. And so let's move on to what we're doing in Elixir at Electric to help you build local first software. And if we come back to this simplified diagram, local first is based on sync. Like that's the horizontal line in the middle between the DB and the server in this diagram. And actually there's two parts to it. You have the read path sync, which is to get the data from the server into the local app. And then you have the write path sync, where you're syncing local changes off the device, usually back into a server or database, but potentially like peer-to-peer or a bunch of different topologies. And the write path has a bunch of very well-known complexities, especially to people who are familiar with distributed systems. You have concurrency challenges, conflicts, difficulties maintaining integrity and user intent. And actually, these are quite application dependent. And so I'm going to come back to these in the next section. And one of the examples I want to show about how you can develop local first with Elixir now is to walk through a number of write path sync patterns. But before we get to, in a way, those hard problems, there is a more fundamental problem that you need to solve, and that's the stale data problem. So the whole point of a local first app is that you have the data locally. But of course, if you have the data locally, then you need a way of keeping that data up to date. So if you take this fetch example we started with and you stick it in a listing page, so you load the data when you render that page, what happens when you navigate away to another page and then come back to the first one? Is the data still up to date? Do you need to refetch it? Do you block with a loading spinner whilst you're refetching? Or do you show what you have and then update it once the new request comes in, causing your listings to flicker and move around? Do you do what Blue Sky does here, and you have a little new indicator when you're notified that there's changes, and you make the user click and they refetch and they scroll and then render up? And without getting too distracted here by the dog whistle of our new fascist overlords, the point is that this is exactly the type of imperative network-aware coding that we're trying to move away from. So instead of you as a developer taking care of keeping the data up to date, you want a sync engine to do it for you. And that, of course, is what Electric is. So with Electric, instead of fetching data like this and then handling all these failure scenarios, you tweak your code to sync data like this, and then the system just takes care of it for you. And if you look at an example application, this is a quick snapshot of a linear clone that we built with Electric. It has 100,000 GitHub issues synced into it, with I think 200,000 comments. They're synced into a local PG-like database. You can filter the app, navigate, all the data's just there. So everything's local, instant. And I think I'm just going to like navigate to a screen, add a new item to the database, you go back to the listings, the item's just there. And of course, it would just be there whether you added it or whether somebody else added it. So the system is just taking care of keeping everything automatically up to date. So as a developer, and from the viewpoint of your application code, you can trust that that local data is up to date. And so how do we do that? Well, technically, Electric is a web service itself. It runs in front of Postgres, and it connects, as most applications do, via a database URL using a standard database user. And it connects using a kind of normal interactive query access, and it also establishes a subscription to a logical replication publication. And then it provides an HTTP API that clients consume over long polling. And that may be surprising. You may wonder, if this is a real-time sync system, why does it not use WebSockets or another protocol? And actually, it's because by using standard HTTP with long polling, we can integrate into existing application stacks much better, and also tooling like middleware and CDN infrastructure. So it actually turns out to be much more scalable, reliable, and better performance to use more old-fashioned long polling than to use kind of newer stateful sync protocols. As I say, it's just an Elixir app, or it's an Elixir application. The source is all on GitHub. I can share links later, but it's on the ElectricSQL GitHub. And basically, it does this scalable fan out of data from Postgres to clients. So if you look at this diagram, the sort of solid blocks from Postgres to client on the right are what Electric is doing, consumes the logical replication feed, and it fans it out into what we call shape logs. And then clients can subscribe to those shapes. And so we do sync, but we do it with partial replication. So you're not necessarily replicating all the data. You can choose a subset of the data that you want to sync into the client. And we do that through this primitive called a shape, where the idea behind a shape is that it's very similar to, say, an ecto query with an association graph. So you can pull in like a tree or a DAG of data, and that's just like a subset of the data from the database. And a shape might be like a project with all of the contents of that project. At the moment, actually, the implementation of shapes that we have is still relatively limited. So it's single tables with where clauses, but we're working towards providing a more expressive shape interface through Electric. The kind of idea is that you can do a richer definition of partial replication. And then in order to deliver that, we leverage the Beam, the Erlang VM, for resilience, concurrency, and we basically do a lot of GenStage-based data processing. I don't know how readable this slide is, but I was digging into the Electric code to kind of what's the best way of illustrating that. And this is a module doc string kind of just discussing kind of some of the supervisor tree infrastructure that we sort of spin up through the kind of pipeline to process this sort of data stream and fan out. So you can kind of get a sense of the sort of type of wiring within the application. It's a bunch of kind of OTP, GenStage stuff, and that's helpful both to kind of harness concurrency, and sort of make the right trade-offs in terms of the performance engineering of the system. And if you look at some benchmarks, for example, this is showing the sync time for a single shape to go to a client based upon the number of rows in the shape, and it goes from like 1 row to 1,000,000 rows. And as you can see, the sync time scales linearly, and important on the graph on the bottom, the memory is relatively flat. It is essentially flat. So like what we've done is try to engineer the system so you don't get this thing where your sync system explodes in memory or any other compute resource when you start to get higher throughput. And instead, we can just handle these things with sort of known flat or linear resource use characteristics. This is another graph here, which just demonstrates with write fan out. So the previous one was about sort of serving data out to clients, and another performance thing is how quickly can we write the data out of Postgres into shape logs, and that determines you have these change messages coming through the logical replication stream. And then the question is like, how many shape logs do you need to write those change messages out to? And what's the expense of kind of doing the matching? And so this demonstrates, again, that it's relatively linear in terms of the number of concurrent shapes that you're writing to. And there's some trade-offs here that I'm happy to go into depth on in Q&A if it's useful. But basically, what I wanted to get across is that we've engineered this core Elixir service to be sort of zero surprises in the way that it scales and uses the compute resources. And then that's the kind of core server itself. But because, as I mentioned, we serve over an HTTP API, we actually scale out the data delivery to clients through existing CDN infrastructure. So think of things like Cloudflare and Fastly. So for this kind of read path sync, there's two aspects of it. You have the initial sync, which is when a client wants to request the data that it doesn't have. It's like subscribing to a new shape, so it has to get all the existing data. And for that, what we do is we query Postgres, we write into a shape log, and then we serve that shape log out, and it's essentially batched arrays of JSON documents. And that allows it to be just served as basically static documents, which can be served through a CDN. And so if you have multiple clients, if you have concurrent clients that are accessing the same data, then they can just be served through the CDN. And so that takes that query workload off not only Electric, but also the source Postgres. And in practice, if you deploy Electric as a system to get data into wherever you're choosing to sync it into, it often radically reduces the query workload on the source database. And then the other aspect is if you have a client that has got a live subscription and it's monitoring for real-time changes, because we use HTTP with long polling, we can leverage a capability of existing CDNs called request collapsing, which is that if a CDN or a reverse proxy that supports this gets multiple requests to the same URL at the same time, it only needs to send one request onto the origin server. So you can have 100,000 concurrent connections coming in at the CDN layer, and only one comes through to Electric. And so that's the way that like the core system is engineered to be scalable and reliable, but actually the data delivery just leverages this existing CDN infrastructure, which is obviously highly mature and tested at scale. And this here is a summary of the sort of benchmarks that we run with a CDN in place that demonstrates scaling out from 1 or 100,000 to 1 million concurrent clients. I think the overall workload was delivering around 80 gigabytes per second. And as you can see, the latency is flat from like the minimum to the maximum number of clients, and so is the memory use of the system. So this demonstrates scaling out to 1 million concurrent clients for a high throughput real-time data workload. And basically Electric is perfectly fine with the compute resource, and the source Postgres doesn't even notice it. So it's a way of running these very large-scale real-time workloads on top of just an existing standard database infrastructure without adding additional resource load or any sort of concerns around exploding compute use for that existing infrastructure. So I hope that gives you a bit of a sense of what Electric is and how we've been trying to approach engineering it and why we're using the Beam and Elixir. So now I'd like to go to the third part, which is to go into some actual code to show you how you can use this. So I'm just going to come out of presentation and jump over. And so I'll just set a little bit of context by looking at the Electric site. So as I mentioned, I'm just going to kill Zoom. I'm not sure if you can see it, but I can. Anyway, so as I mentioned, we send data out through this HTTP API. You can see here, for instance, that this was literally just a curl request in terms of how you use the system. Now, if you think about doing this read path sync, there's two other aspects that you then would need. One is authorizing access to the data, and then the other one is how you do the write path sync. And so those are two of the examples that I want to show you, but also just in terms of using our core API. So this is the kind of underlying HTTP API, but of course that's wrapped up into client libraries. And so like this, for example, is our core TypeScript client library. You establish a shape stream, you materialize it into a shape, and then you can just basically get notified when it changes or just access the materialized value. And that, for example, is what underpins the use shape hook that I showed you previously in terms of changing the code from fetching to sync. And then, but we also have a first-class Elixir client. So again, using Elixir, here we can establish just an electric client subscription to a shape, and you just consume this stream and you can materialize that stream into a data structure. So Elixir for us is a first-class kind of client platform for Electric Sync. And then for a more comprehensive integration, we have a Electric Phoenix package where it does two things. One is that it integrates in to the Phoenix Streams capability of Phoenix Live View. So what this does is allow you to, if you're taking a collection and passing that to the front end of the live view, rather than just having a static collection, you can use this electric stream function instead, and then electric just keeps the function live for you. And the Phoenix Streams mechanism, which makes it efficient to update collections over the wire to the front end without having to hold the whole collection in memory on the server side, we actually tap into almost one for one in the sort of types of messages that come over our replication stream and that you would serve over the Phoenix Streams API. And so what this does is it allows you to basically make live view applications which bind to shapes out of your Postgres database and then are just real-time out of the box, which is a very cool mechanism of building real-time software without having to write any JavaScript whatsoever. And I'll jump in and show you an example of this. But that's cool, but it's not kind of fully local first in the same sense. And so what we've also done is, I don't know, you may be aware, but Jose Valim did a Elixir keynote a while back introducing his vision of a library called Phoenix Sync. And we've worked with him to effectively implement Phoenix Sync using Electric. And so what this does is it allows you to integrate Electric into a Phoenix application and serve shapes based on Ecto queries. Again, I will just dive into an example that shows you that. But basically, this is a way of exposing sync through a Phoenix application. Now, those two key aspects of development that I mentioned before, so auth and write. Now, with authorization, when you use a sync engine, most people would think that you would have to use some kind of rule system to authorize access to the data, because in a sense, you sort of lose the flexibility of that end layer. But with Electric, because we sync over HTTP, you can still route the stream through a proxy. And so you can use a proxy as an authorizing proxy to control access to the data. So when you are saying, I would like to sync this shape into this client, or if a client is requesting that shape, you can say, okay, what are your credentials? Which shape are you asking for? And you authorize access to it just the same way you would authorize access to any other web resource. And of course, you can use any web framework for that, including any Elixir framework, but it works very well with like Plug. And if you have an existing application that's been built using Phoenix, where you may have, say, a Plug-based authorization middleware, it's very easy to repurpose those to use them with Electric, as opposed to having to work out how to codify them into something like RLS or Firebase rules or something. So that's a key aspect of in practice, in reality, when you're deploying this stuff, you need authorization, and Electric is designed to be able to be used with the authorization primitives of your existing web framework, including Phoenix. And then with write, as I mentioned previously, there's a fair bit of complexity and concerns around, say, concurrency and rollbacks that are kind of quite well understood around this type of system. Electric doesn't prescribe a solution to write, and instead we document here a number of patterns where you can implement some different approaches to the write path of your application. Now, I'll walk through an example of these patterns, but the key thing is that they all work by essentially posting data to your API so that you can use your existing API to handle those, write them to the database, and do any authorization on the right path that you want. So again, Electric is designed to work alongside an existing like back-end web framework, which can be anything, but works very well with Phoenix. And again, you could be reusing similar authorization middleware for kind of read path and write path if you wanted to, and just repurposing or reusing the existing layer that you use to handle writes in your application. And in fact, with some of these patterns, you can just use exactly the way that you would do writes for, say, an API-based application, and then use Electric alongside on the read path and still get a fully local first application. So I'm just going to now dive into some code. So this is our repo. We have an examples folder. You've got a bunch of examples in here. The first one I wanted to show is just the our Phoenix Live View example, which uses that Phoenix Streams integration. So this is a Phoenix application. If I go in to just show you the code, it's a to-do list app. We have like this is a live, and here, for example, we're just showing you that when the live view mounts, we use Electric Stream to send the result. So this is actually basically sending an ecto query by just saying query all of these to-dos, and that gets streamed through us the to-dos collection into the client. And then in here, we handle writes inside the live view just the way you would do it with a normal live view, which is just we're handling events. And so like here, deleting or toggling completing. I think this is the actual form component for adding a to-do, and you can see here it's just like there's just standard code for adding a to-do. And so basically if I fire this up, and then just jump into it, here it is, and it's just a standard to-do list application built with live view. But the key thing, of course, is that it is just naturally real time. So one of the things I can do here is if I just pull up another web browser, you can do the kind of standard real time thing, and it just gets the same data. And if you write in one, you write in the other. And you can just sort of interact with them as you wish, and all of the data syncs, of course. Now, another nice thing of the Electric system, of course, is it's all just Postgres. So everything just syncs automatically out of Postgres. So you can write through an application like this, but you can just also write directly in Postgres. So if I just open up a PSQL client to the Postgres, and if I wanted to, for instance, set all of these to-dos to, I just wanted to get it so you could see them at the same time. Let me just move this up. There we go. You can just update the database and everything just immediately syncs through. So it is a very nice way where there is basically zero additional wiring to your application to make it real time. And there is no silo in your data model. It is just Postgres. And you can have any application writing to Postgres and everything just syncs. So this is a pretty powerful and productive paradigm for building real-time applications in Elixir. But if we were to jump through to a more local first example. So what I'm going to do is I'm going to run an application which basically runs all of the different write patterns that I was just showing before. Now, before I do, what I just want to show, I want to show another one, an example around auth, where one of the patterns that we have for auth is to use your Phoenix application as a proxy. And here we have a Phoenix application in this gatekeeper auth example that implements that. If I just jump into it just to show you, it's basically you have a gatekeeper endpoint which uses this Electric Phoenix library to expose streaming a shape through your Phoenix application. And then we just have a proxy endpoint here. So sorry, this gatekeeper application generates authorization tokens, and then this proxy endpoint actually streams the shape through. And this is just set up as a standard Phoenix router. And here there's two pipelines, and they basically just use plugs to do the authorization logic. So the pattern, I can show you a little diagram of it here. somewhere. Yeah, here. So if you can see this okay. So basically the pattern with this app is that the client wants to stream a shape, but you are protecting access to the API through which they can stream the shape using this gatekeeper endpoint. So you would post user credentials to the gatekeeper endpoint saying, hey, this is me and I'd like to stream this shape. The gatekeeper endpoint then returns a JWT, which is actually a shape scoped authorization token. That is then added as a header to the request where you're wanting to proxy the shape stream. If that's authorized, then you make the request to Electric and then you stream the data back through the proxy. So that's the kind of flow. Now, the key thing is that if you actually look at this, we have a plug here where we do a little bit of Electric specific stuff to go with the Electric API. You define your shape in your request parameters. And what we do here is we basically just go assign the shape to the plug context, to the plug assigns based upon your request parameters. And then when it comes to the gatekeeper endpoint, we pipe through a gatekeeper pipeline that assigns the shape. And then we basically have two just fake things to go authenticate the user and authorize the shape access. Authenticate the user is just dummy. You just assign dummy to current user because this is an example. And then when we authorize the shape access, basically we're just saying if it's the dummy user, it's authorized. But this is where you could do any kind of arbitrary logic to go, is this user allowed to access this resource? Because you have the current user available and this is just standard middleware code. And then when it comes to the proxy, we're then able to authorize the token that's returned from here, where we have a pipeline that says, okay, again, get the shape from the request parameters and just verify that the token is authorized to access the shape. And that's kind of what this verify token does. It goes just authorize it. And we have this authorizer class where it basically generates out a token, a shape scope token, and it authorizes that token. So I know I'm going through this quite quickly and there's quite a lot of specifics here, but I just wanted to kind of show what I hope looks to you like very standard Phoenix code. These are standard endpoints. These are standard plugs. This is how you can achieve authorization. And in addition, if you imagine that you wanted to handle writes in the same application, it would be very, very easy for you to just expose APIs alongside this within your application, just as you normally would, right? Like here's the actual proxy controller implementation, but you could easily have a write controller and you'd just be able to use the same middleware to authorize writes. So I just wanted to jump into that code to give you another context of kind of how to do that sort of authorization pattern. Now, if we move on to writes, let me just basically fire it up so you can actually see something. So in the write patterns here, I'm just going to basically run the application. And here we go. So what we have is we have these four apps all just sort of embedded within the same app, or they're just React components, all part of the same React app. And they all implement the same to-do list application, but they do so using a sort of progressively more complex write pattern. And so in all of these applications, it's using Electric to sync. So like we saw before, you add to one, it syncs into the others. This is all going through Postgres, obviously. Now, what you then get is that the first pattern of going, okay, Electric does read path sync, but how do I do the write path sync? Is just to use a normal API to do writes. And that's what this online writes example shows. So it just basically posts data to an API to write the data. So if we look at the source code here, this is a React application. This is our function basically for that app. We have our use shape hook, which is syncing data in from Electric. That's where the data comes from. And then here we have three functions, which are like create to do, update to do, and they all just basically like just do a standard CRUD operation by posting it to an API. So create to do, update to do, delete to do. And then down here, we just have the kind of interface in React for like render the to-do list. And if you click it, it toggles the to-do, and if you delete it, deletes it, and there's a form here to add it. So that's what we're just seeing in the page here. And you can imagine the API that's handling that just being a Phoenix API. Now, The downside of just doing that, of course, is that the application requires the API to be online. So if we look at how it behaves if we turn the network off, so I can go here and set this to offline. Now, we've sort of done the best we can because we have a resilient fetch client. So basically, we can see in the network tab that that request has failed, but it is backing off. It's both trying to sync the data from the client, sync the data on the read path, and trying to make that right. And so if I turn it back on, the kind of best we can do with this simple online example is that once the back off algorithm sort of catches up, the write goes through, and then when it goes through, it'll sync back to everyone else. So that's an example where you do still get some offline resiliency, even just without handling any kind of optimistic state. But a slightly more realistic example, which doesn't require too much boilerplate, is like if we look over here, we have this optimistic state pattern. And so here again, I can just like sync an item. Now, if we look at the code for the optimistic state example, it's very, very similar. There's two differences. The first one is that we import this standard use optimistic hook, which is available in the latest React release. And we import something to be able to monitor the replication stream to kind of see when our writes are synced through. And so then what we do in here is it's basically a component again, and we use the use shape hook just to sync data in. All of this is very similar. And then the difference is that we have this built-in use optimistic hook, which provides you this function so that when you're doing a write, you can register some optimistic state. And then all that this is doing is basically merging that optimistic state into the to-do list that's being rendered. So if it's an insert, you add it to the list. If it's an update, you patch the properties. And if it's a delete, you remove it from the list. And this is very standard stuff, right? There's now built into React. It's a kind of blessed pattern. It's sort of very common. It's maintained. And then these create, update, delete functions are basically exactly the same as before, except that rather than just doing this here to post the data to the back end, we do it inside a transition. We first add the optimistic state, then we make a post request to the server, and we also monitor the replication stream for that write coming through. And then what this allows us to do is basically display the write to the user instantly so that the application functions for users offline while still basically waiting for the request to go through. And so if we come back here to this example and I turn this off, then it does what you expect, which is that the state is kind of here, shown to you automatically. This little spinner is showing you that sort of transition still active. And then if I turn it on, then it'll sync. It basically syncs through, and it removes the optimistic state, and it syncs through to the other applications. So this is very, very little boilerplate on top of a kind of basic pattern for doing an API-based application, but you already have an offline capable, essentially sort of partly local first application. Now, the next pattern, there's two more patterns here, which I'll go through, and they are maybe a little bit more powerful. The shared persistent approach extends this idea of optimistic state, but the weakness of this use optimistic approach is the optimistic state is just within the component. So it's not persisted, and it's also not shared with other components. So this shared persistent example, we do again, just extend things a little bit where there's a little library here called Valtio, which is just like a reactive local store. So that's a way of having a very simple in-memory key value store that you can also just subscribe to changes from. And we still import the React transition, and we still have these matching stream utilities. And so what we do is we just say, right, the optimistic state is a instance of this Valtio store, and we also persist it to local storage. So basically, when the application loads, we hydrate it out of local storage, or when you write stuff, you write it to local storage. So that's the kind of additional code to basically make this client-side store for sharing optimistic state across components. And then because this is a slightly more realistic pattern, we've also made our matching logic a bit cleverer so that instead of just matching on the row ID, we generate a unique ID for each write. And that allows us to do slightly more sophisticated merge logic, because we can apply the local optimistic state on top of other concurrent operations from other users, and we only remove it when our write syncs through the replication stream. So these patterns are just showing a sort of slight increment in the complexity of the merge logic with these optimistic writes. So basically we have a function here of like adding a local write to the optimistic state. We have a function for matching a write, and then we have a function for making a request. And then basically everything's exactly the same. So it's a transition, it's the use shape. We have a very, very similar function here for just applying the optimistic state. It uses this Valtio store, but otherwise this sort of merge logic is exactly as we saw before. And then these functions are almost exactly the same. So it's just create to do, and then we start a transition and we apply the local state, and we make the API request and we match the stream, but we match it in a slightly cleverer way. So again, it's very little additional code on the example that we were just seeing, but what we get with this example is really quite a comprehensive local first application, because you can have multiple components that are all sharing this client-side state. The pattern is that you sync into the data. The data that you sync is immutable from the server, and then you have this mutable local optimistic state that's merged on top of it, that's removed once your writes have been confirmed as syncing through the replication stream. And as you'd expect, the behavior here is like the same. It's obviously you can just write and it displays it instantly, and you flick the thing on again and it kind of the write goes through, and then it syncs through to the other applications. And then just the last thing that I wanted to show is then this through the DB sync pattern. So, I mean, typically syncing through a local embedded database is regarded as quite a complex challenge. And what we've tried to do with this pattern is show that actually it can be relatively simple. And in this case, what we do is we make writes to a local embedded database, and then we detect those, and then we post change sets to the server. So it's not quite the same as just doing exactly the same as you might do with like a REST API handling a write. You would have a slightly different write endpoint, but actually it's still something that would be very straightforward for a backend Phoenix app to handle. So a lot of the complexity in this example is based on a local embedded PG Lite instance in the web page there, and this is the schema for the local Postgres database. And the trick is that where you have a table, you actually have two tables. One is where you sync the state from the server and you treat that state as immutable, and then you have basically a shadow table for local optimistic state. And then you can do some trickery in your database schema to combine those into a view, so you can then query it as just a unified table. And you can also use, instead of triggers, I'll just jump down to the, so here, this is an instead of trigger that basically says when you do a write operation, it intercepts it, it writes it to the local mutable store, and it also writes it to a change log that you can then sync. So there's a bit of scheme here that's probably a little bit too much to go through in more detail, but it's about 350 lines of SQL, and it's very, very generatable. So like this is handwritten SQL, just demonstrating doing it by hand, but it would be very easy to make a generator for this for when you are creating a table. It sort of emits this kind of boilerplate. And basically it also, when you stream in a new item to the synced tables, it basically looks for the optimistic state, looks for this matching on this write ID, and removes the local optimistic state. So the optimistic state is removed in almost exactly the same way as the last example with the shared persistent pattern. And with that complexity there, if you actually look at the application code, it is extremely simple. So we have a little bit of PG Lite boilerplate to instantiate PG Lite, but then if you look at, and that's what this wrapper basically does, it just instantiates the local embedded database. And it also instantiates a sync utility, which I'll just go through next. But then when you come down to the actual component that we were looking at, as per the other examples, you get a handle on the local database and you use a live query to just get the to-dos. and then that's it. You have these, you can just have functions where you just write directly to the local embedded database. There's no need for any awareness of optimistic state. There's no sense that that operation could fail for some sort of network reasons. You're not coding across the network. This is literally a embedded local database in your application. And so it's very, very simple to just use SQL to insert, update, delete. And that's that, basically. And if you look at the behavior again with the application, it's just exactly what you expect, right? Everything's just instant and it syncs through, and obviously it's supported offline. In this case, we don't have the same spinner because it's just not needed, because actually the operations are accepted into the local embedded database. And so, you turn it back on and everything syncs when the network just comes back on. So, I mean, this is an example of a very proper kind of full local first application using an embedded database where authorization and rights could be handled through a Phoenix application, and the read path sync can be an Electric instance embedded into the Phoenix application. And again, there's just one little extra bit, which is that we have a little utility here, which just monitors a change feed table and posts them to an endpoint. So there's just a little bit of sort of control flow logic to monitor this table. And then basically we batch up changes and send them through as an array of transactions to the back end. But as I say, it's a relatively, you're then just basically going, okay, I've got a batch of transactions. What do they contain? It's a write to this object. And so if you want to go, does that user have the rights to write to this object? You could just do that on an operation by operation basis. And if you reject the rights, then the local schema has got the stuff built in to be able to go, okay, that right was rejected, so we can roll back the local optimistic state, and the application is always in a consistent state. There we go. So I hope that was interesting. Very happy to answer any questions on these examples. Maybe just to note again, if it's interesting, so electric-sql.com, we have a Discord channel which you can join. There's about 2,000 people in there, and this is our GitHub here. We're GitHub electric-sql, and you've got both the Electric repo and PG-Lite, and PG-Lite also has its own website and documentation here. And so that was that, and I hope that if I come back to it, I've convinced you that local first is a better way of building software applications. I hope you understand how the Electric Sync engine fits in to being a component that can help you compose a stack to build local first applications. And I hope it was interesting to see some of the primitives that we built to use that in Elixir, both the Elixir client and this electric.phoenix library, which is up on Hex, and you can just sort of follow the documentation for. Thank you.
Thank you very much, James. Thank you for a very nice presentation. People are saying like they like it. Thank you very much, James. Cool. First question. Where did you get the idea to build like local first? What was like, was this something I need it, I want it?
Yeah, I mean, it's interesting really is that when we started the company, we were building on research into distributed database systems. So like not me, but a number of my colleagues and our advisors had invented a lot of stuff to be able to build systems with more consistency and integrity on top of active-active replication and the sort of AP side of the CAP theorem. So our first idea was like, let's build CockroachDB, but for the AP side of the CAP theorem. So that's sort of where we started. And actually we were building on a Erlang-based system called AntidoteDB, which was a prototype that the academics that we were working with had built, or slightly more than a prototype. It was actually really quite well built and maintained system. But then you sort of dive into like, okay, but how do people want to use this, and which problems are we solving for people? And we sort of rethought of using the same algorithms to do a replication layer behind existing open source databases. And so you had this idea of like active-active Postgres and Postgres to SQLite. And then we were digging into use cases for that. And that's really where we realized that there's quite a lot of people in this emerging local first software space who are trying to build on these types of patterns. And we sort of, again, reconceived what we were doing as a sync layer over this sort of last mile state transfer between the client and server kind of setup rather than like a sort of distributed multi-region database. So that's slightly how we stumbled into local first. And we then spent like a while trying to build a more integrated end-to-end local first software stack. But then last summer, we sort of got to the point where we were getting a bit bogged down in the complexity of that, and it was just a bit too much to deliver on what we were trying to do. And so we've simplified what we're doing back down to this read path sync and tried to make a much more composable system that we could actually productize and people could build applications on. So it's been quite a sort of journey of, in a way, sort of stumbling into the area, understanding which problems were solved and which ones weren't, and sort of trying to build software that's useful for people.
Interesting, thank you. You mentioned at some point, like you made a choice of Elixir or building on the beam. Did you ever consider anything else, or was it like, no, we're building it on the beam and that's it?
Yeah, I think the sort of truth is that certainly for me as an Elixir developer coming into the project in the kind of early days, it was such an obvious fit. And also when we were first building on AntidoteDB, which was based on the beam in Erlang, like we sort of started off with ideas of going, well, how would you integrate AntidoteDB into a library like Ecto? We actually like built out a library called Vax, which was kind of doing just that. So our earlier ideas were that we wanted to sort of take the underlying research stuff and make it accessible to Elixir developers. Now we're much more of a sort of generalist platform where you can use this from any language, and a lot of people are using it from JavaScript because that's how more client systems are kind of built. But in terms of the actual sync engine itself, it's such a fantastic fit. I mean, we really do lean very heavily on GenStage, OTP, supervision trees, concurrency. That probably in the beginning it was just kind of such an obvious choice, didn't really overthink it, but it's not something that we've ever kind of thought about changing just because it's such a fantastic match.
Thanks. Final question. Is there any competition or like alternatives or other like solutions to this?
Yeah, I mean, there's some very cool projects, and there's a lot of really cool projects in this local first space that are well worth checking out. There's like a lo-fi Discord, which is really good for kind of like picking up on a range of projects. They have a website as well, which was called Local First Web, or kind of lo-fi software. And there's a variety of projects from different angles. Like there's cool projects I could list off would include things like Zero. So there's a project called Zero Sync, which is by the developers of Replicache. And that's a fantastic also sort of Postgres based sync system, which is doing quite a lot of clever stuff to sort of manage how data is synced into the local client. It's a bit more end to end integrated and sort of smarter about how it manages sync for you. There's a great project called Jazz, which is a sort of batteries included local first stack and sync system. There's one called InstantDB, which is a little bit more sort of graph orientated and sort of viewed as like a successor to Firebase. But they've done some very clever differential data flow based kind of sync stuff for sort of partial replication of a graph model. And it's still persisted in Postgres, although it doesn't work with the sort of existing Postgres data model out of the box. You sort of adapt it to their data model. I mean, and there's a lot of others. PowerSync is also another system which does this type of local first sync on an existing Postgres model. And that's quite mature and has been had a lot of people using it for a long time. So there's a lot of these really quite cool projects in this space because I think a lot of people have seen the patterns. Some of the underlying challenges have been kind of solved. And it's sort of clear that as an application developer, like for example, like Figma and Linear famously spent millions of dollars developing their sync technology because they wanted it to be a differentiator of their products. And it's really worked because they've been able to make really high quality products. But when you look at it, actually it shouldn't be that every application is building its sync engine. It should be the sort of type of thing that can be solved by a framework or a library for you.
True. Maybe it will be commoditized in the end, meaning that it will converge to a separate. I don't know.
Well, Martin Kleppmann, for instance, So there was a local first manifesto paper that was written by Ink and Switch, which is a research lab that has sort of pioneered a lot of the thinking around this, and Martin Kleppmann is part of that. And one of his visions for local first is a standardized sync protocol. And so it's quite interesting to sort of think, yes, a lot of the ambitions behind local first are around, there's these sort of there's considerations around like just making faster software and sort of better UX and better DX, but you also have aspects of data ownership, and you don't want to have to kind of give your data to the cloud and have that exploited. And so with that sort of more ethical mindset on it as a software movement, you also want to think, okay, how do you have, say, data interoperability? And so that's like, there's a bunch of thinking that Martin's developing around that kind of like, what would a shared sync protocol look like for local first software, that I think is going to be really influential.
Again, thank you very much, James, for today. Thank you very much. People are giving you big thanks in the chat. So thank you very much
Awesome.
again, James. Yep.
Thank you all. Yeah, great to be here. Cheers.
Yeah, you're welcome. You're welcome. Thank you.